Welcome back to Bio 6612. In the final lecture of this week, we're going to talk about missing data. In particular, we'll focus on types of missing data in longitudinal studies, and briefly how GEEs and GLMs handle missingness. The textbook by Widdinghoff, which is on the course website, actually has a nice chapter on missing data. So if you want more, I definitely encourage you to read through that chapter. So missing data occurs in biomedical studies all the time and can be due to a lot of issues, including subjects refusing to answer sensitive questions like those related to, say, drugs or alcohol, or other personal questions. Subjects dropping out of a study, say because a drug that they're on is uncomfortable or they get really sick. Or data entry areas, to name just a few ways that missingness can occur. And oftentimes, statistical computing packages drop all observations that are missing in any of the variables, the outcomes or predictors that you specify in the model. This is what happens with LM. And when this happens, this is called the complete cases analysis, or complete case analysis of your data, because it deals with only observations or rows in which you have no missing values in the outcome or any of the predictors. And in a lot of cases, this is fine, but in other cases, this can lead to a bias because if missingness is happening because of something that's related to the covariates or the outcome of interest, or it can lead to a decrease in power because it causes you to lose sample size. And missing data is very common in longitudinal studies, especially at later time points in the study. And this is often due to dropout over time, where people initially enroll in the study but don't stay in the study for a host of reasons, including what I mentioned before, where sicker patients may be less likely to show up for follow-up visits. And as a whole, we should always be aware of why data might be missing in our study, how it is missing, and how our analysis method handles missing data by default. And to look into this, we're going to go into the HERS data example, which is from the Widdinghoff book. And there's also a paper that I've linked here, which is the original paper for this clinical trial, which was a clinical trial called the Heart and Estrogen or Progestin Replacement Study, which they called HERS, which looked at a randomized trial that determined the effects of estrogen replacement compared with placebo on cardiovascular disease in postmenopausal women. And it went on for about 6 years. The data is available online, but I also put it on Canvas, and you could install it using the read Excel statement, and I'm also cleaning the names here. I'm just making them to be all lowercase because I like that style better. That's what that function is doing. And the data has 15 variables, which I'm not listing all out here, over 9,000 observations and over 2,000 subjects. So this was a big study. And there are 6 different visits. There's 0, which is baseline, and then 1, 2, 3, 4, and 5 years of follow-up. And they actually looked at a couple different outcomes in this study, but just for our purposes, we're going to consider systolic blood pressure, which is labeled SBP in the data set, to be the outcome of interest here. So first, let's look at a little bit of missingness in this data. I'm using a chunk of code here to produce a table of the numbers of explicitly missing values in each variable of the data set. And by explicitly missing values, what I mean is there's an NA there. And so this table gives the number of NAs that are in each of these different variable columns. For example, the BMI variable has 45 NA values. And the glucose variable is missing a ton of values. So that might be a hard variable to use in this analysis because it would cause us to lose a lot of subjects, at least if we're using the complete cases analysis. And what you'll see here is there's no SBP variable. Does that mean that there's no missing data for SBP? The systolic blood pressure, the outcome? Well, not necessarily, because we can also have implicitly missing data when we're looking at longitudinal data. But because data is in long format, we won't see rows where people didn't show up for later visits. So let's say you showed up for visit 0, 1, and 2, but you didn't show up for 3, 4, and 5. You're not going to have rows corresponding to visits 3, 4, and 5, but you're still missing values of the outcome and all the other covariates at those time points. So that still counts as missing data, even though there's no NA value there. But in order to analyze the patterns of missingness that for data that for outcomes that are missing for when we had dropout due to follow-up, I am expanding the data set to sort of fill in NAs for when people didn't show up for a visit when they were supposed to. And that's what this code is doing here. So it's producing a new data set called SBP missing that only has the patient ID variable, the visit variable, which indicates which visit number we're on, SBP, which is the outcome, and then this SBP measured variable, which is a binary variable indicating whether or not they actually showed up at that visit. So it would have been an NA, and NA here corresponds to a 0. And you can see that for this first patient, they showed up for their the baseline visit, and they showed up for visits 1, 2, and 3, and that corresponds to the ones here because they showed up for all of those visits, and they have values for the systolic blood pressure at each of those visits, and it seems to mostly be going down, but they have NA values here at visits 4 and 5 because they did not show up for those visits at the end of the study. And so what this SBP missing data set is doing is just showing us explicitly now where we're missing values for each of those SBP outcomes. And one of the reasons I like to expand the data to that format when I'm trying to examine what's going on with the missingness is, actually one thing I'll mention though is I defined a new data set here because I'm not going to use that one for analysis. I'm just using it for exploring the missingness in the data. And one of the reasons I like to put in that format is because then you can actually visualize the missingness in a nice heat map. And the way that you interpret this heat map here is each row is actually a subject and each column is a point in time. So you have first visit, visit 0, visit 1, visit 2, visit 3, visit 4, and visit 5 on the x-axis here. And 0 indicates that they did not show up for the visit. So red indicates they didn't show up and blue indicates that they did. And I also sorted these by their sort of percent adherence, so how often they showed up. So you can see here that those are the people who showed up for every single visit. And it's actually not a huge proportion of this data set. So if we were going to only use a complete cases analysis, these are the only people that we would be able to even consider using because everyone else has at least one visit that they didn't show up for. Then all of the people who are in this chunk, as well as these chunks down here, showed up for all but one visit, and the one visit they did not show up for was the very last visit. You have a couple people sort of scattered in here who showed up for all but one visit, but their pattern is different. Where I pointed these arrows, these are people who didn't show up for the 4th visit, but then came back for the 5th visit. So they in total missed only one visit. And then towards the bottom here, you have people who didn't show up for that many visits at all. At this little smaller chunk, you have people who showed up just at baseline and then they never showed up again for the rest of the study. So these, I think these are helpful for sort of interpreting the patterns of missingness in your data. It's a little bit complicated the way that I actually made this plot, but the first thing that I did is I grouped by the patient ID to calculate the percent adherence for each subject. That's so I can actually sort the plot by how often people are showing up, because that really helps to, I think, visualize the patterns and how many people are adhering to each. And I calculated that by summing up the total visits that they have a 1 for that variable indicated whether they showed up or not, and then divided by 6, which is the total number of visits. then I am using this, I'm factoring the patient ID and the systolic blood pressure measured variable. And then I'm using this factor reorder function from the forecats package to reorder the patient IDs by percent adherence. So they'll be factored by lowest to highest percent that they showed up for visits. And then finally, I'm using ggplot, and I'm using this geom tile function to produce a heat map. So those are just some basic ways of visualizing some missing data, but there are a couple different types of missing data. And a common practice with missing data in a longitudinal study is to look at baseline characteristics of patients who had missing data later in the study. So the three common classifications of the missing data process are MCAR, which is missing completely at random, MMAR, which is missing at random, and MNAR, which is missing not at random. First, missing completely at random is sort of what the best case missing data. And this is when missing values in the outcome are considered completely independent from outcome values at other time points or values of covariates in the data set. So in the context of our HERS data set, this would mean the probability of missing your blood pressure at visit 6 is completely unrelated to the value of blood pressure at visit 0 through 5 and unrelated to values of BMI, age, weight, and other covariates. Basically, the probability of the data being missing is not associated with any part of the data, with any other part of the data. And the reason that we say that this is the best case is because it means that analyzing complete cases where you will not in any way bias the analysis. So you can kind of use any type of analysis you want, and it's not going to be biased due to missingness. However, this assumption is usually pretty unreasonable to actually make. It's usually pretty likely that people are dropping out for some reason, whether that reason have to do with data that you observe, such as, say, everybody on one treatment is more likely to drop out than people on the other treatment, or due to things that you can't see, like maybe everyone dropped out of the study because COVID happened and they live in a densely populated area. I don't know. There are lots of reasons, but there's usually some reason that the data is missing, and it's not just totally random. So another sort of assumption about data missingness you can make is missing at random. And this is an assumption that handles a variety of more plausible missingness scenarios. And in this case, the probability of missing data can depend on either the covariates in your model. The probability of missing data can depend on any of the covariates you observe in your data set or on observed outcomes. So this allows for people, for example, who are sicker at visits 0 or 1 to be more likely to drop out of the study, or for men to be more likely to drop out than women, or for there to be fewer answers on a survey questionnaire to sort of delicate personal questions to standard questions. And when data are missing at random, and you correctly specify your model, meaning you have the right mean structure, basically the right covariates and interaction terms, then your likelihood-based methods will give you unbiased answers. So that basically means, when your data are missing at random, you can use likelihood-based methods and not worry too much about unbiasedness. And what is a likelihood-based method in the terms of longitudinal data analysis? Well, your generalized linear mixed models are likelihood-based, where your GEEs are not. So you can't. And finally, the last type of model the last type of missingness is missing not at random. And in this case, the probability a data value is missing depends on unobserved quantities. So basically, missingness depends on covariates or outcome values that we didn't observe, either because we didn't measure them in the first place, we didn't collect that data, or because those variables they depend on were also missing. And in practice, this is actually very hard to deal with. And when data is MNAR, any method of analysis may be biased. So we tend to just sort of hope that we have MCAR or MAR data and really try to not have data be missing, not at random. So I've introduced a couple types of missing data. How do we actually handle it? There's actually a ton of research out there about handling missing data, and I'm not going to go into the details really at all, but they're just at a high level. First thing you can do is ignore it and just do a complete cases analysis. And in a lot of cases, that's fine. If you don't have if you have very little missing data, that's probably okay. Or if you know that you are missing completely at random and there are actually hypothesis tests out there you can conduct to check for this. But if you have data that you know is not missing completely at random and you have a decent amount of missingness, you really shouldn't ignore it, especially in the case of longitudinal studies where that might seriously decrease your sample size. Okay, so another thing that you can do is include a missing data category. And this really works better if you are missing in a categorical predictor rather than missing in some kind of outcome. But you can just define a separate variable with missing value that sort of is an indicator of whether or not you're missing values for that particular variable at that category. And this is generally not recommended because, surprise, it can introduce bias. So another common one is called the LOCF method, which stands for last observation carried forward. And this is actually pretty popular. You see it fairly often in clinical trial analysis. But what it does is, let's say that I'm in a clinical trial and I'm supposed to be observed for 5 time points, but I only show up for the first 3. With last observation carried forward, they'll take my third measurement and then they'll just impute that, make it use that number for both the 4th and the 5th as well. So they'll take the most recent, so if there are missing values, they'll take the most recent one that occurred and sort of just impute that into the missing value. And it's pretty simple to do, which is why it's popular. And for reasons that I won't go into, but you might learn about in clinical trials classes, you sometimes want to analyze what's called the intent to treat population, which is the entire population regardless of missingness. And then you need to do some sort of imputation. However, this is also not recommended in general because it can really bias your results if the missingness is not completely at random. So another simple imputation method is taking the mean or median imputation. That is sort of calculating a single number for missing values based on other data that you have from that same data set. And then what's considered sort of the best method is multiple imputation, and there are several actual approaches to doing this, but it just can be more time consuming and computationally expensive. So finally, what to do when you have missing data for GEEs and GLMs. What sort of assumptions are they making about your data being missing? Well, one thing that's nice is both models are reasonably robust to at least some of your data being missing. They don't assume that you are going to use your complete cases. And so that's good because data is prone to be missing when you have longitudinal studies. But what assumptions are they making? Well, GEE's estimates are consistent if the values are missing completely at random. So basically, GEE wants your values to be missing completely at random. And on top of that, it assumes that by default, that observations are equally separated in time. GLMs, on the other hand, are consistent even if missing at random, as long as your model is correctly specified. So GLMs are slightly more robust. for missing data when it's not missing completely at random. So that's just sort of one. I think GEEs can be nicer in terms of their population level interpretation, especially when you have non-identity link functions. But on the other hand, GLMs can be better when you have like really very unbalanced data or a lot of missingness. So it's really useful to have both tools in your repertoire.